Hi, my name is Dan Rosnova. I'm a Senior Program Manager in the Hyperscale Compute and IoT team, and I'm here today to talk about designing and sizing a global-scale telemetry platform on Azure Event Hubs. Today we're going to cover what telemetry really is, especially in the cloud context, why it's so important now, how Event Hubs makes it easy, and how to scale your telemetry for a global application. And we'll end with how Azure services add to your telemetry pipeline to give you more value. Telemetry has never been more important than it is now. Especially with cloud computing, it's more necessary than it ever was in the past, and it's also more valuable. But it's also more complex than it's ever been, and it's a greater challenge than it's ever been. So how did telemetry become so complex? It's really a simple concept. Just track what's going on and where. We really have to go back in a little time travel here and see where this came to be. If we look in the old days, we see the mainframe architecture, which was common for computer systems. Everything was in one place. There was one clock that ruled everything. It was very easy to make sure everything was in order. The terminal screen, the green screen here on this, was never actually even a client itself. It had no capabilities of its own. It wasn't usually even on a network. So this is a fairly easy system to implement telemetry and tracking in. After that, in the not quite so old days, we got into the client-server architecture. And this actually broke the telemetry into two different places. Client telemetry based on what the user was doing, what they were experiencing, and server telemetry. More recently, that broke out into a three-tier architecture, or a tiered architecture, three-tier being the most common. And we divided the application server from something like a database server, it's the most common approach. And now we had a proliferation of logs. There are logs on the client, there are logs on the application server, and there are different logs on the database server. And to make this even worse, you have many clients, each with their own logs, and many application servers and database servers as you scale this architecture out, which is one of its key points that made it so useful. More recently, we've moved to SOA, and still very popular in the enterprise space, and this actually compounds the problem even worse. We have more of an integration approach, and many systems tied together through some sort of integration platform, and each of these systems are usually a tiered architecture of their own. So now you have logs that you don't even know about in places you don't know about. And it's very, very hard to figure out exactly what's happening when you look for problems in a system. The closest you usually get is tracing what's happening in the integration layer, which is only part of the problem. Then we get to today, at the cloud. And now it's not so clear. Cloud workloads are very dynamic. You might have scaling up and down automatically in your cloud system. Components can be running in different places. There might be services that you don't run yourself and that you use from others. You're going to mix things like PaaS services and infrastructure as a service with software as a service. So you have different types of logs with different characteristics, but they're all still necessary for your cloud system. Undoubtedly, cloud has improved our computing landscape. It's increased our agility and our capabilities. You look at small companies today, can grow to global scale with very few employees. You can think of some of the most famous startups in the last few years in that way. But visibility and measurability have often come at a price when moving to the cloud, especially if you don't plan for it carefully. And this really shows itself in any of these architectures when someone says it's slow. What do you do when someone comes to you and says it's slow? In a distributed computing system, and cloud is the ultimate edge of distributed computing, it's really hard to see what slow means. You have one extreme, which is the user, and then one extreme, which is individual service components, or even physical components in that system. So before I talk about that, I need my Zen moment for the day, which is that what you can't measure, you can't manage. And really, that's about continuous improvement and quality management, so you can always see how your systems are reacting. The good news is that Event Hubs makes telemetry really, really easy, even at a cloud scale. It's easy to deploy. It's easy to scale. It's easy to integrate with other services or to write to and read from, and it's very, very cost effective. So let's walk through a very simple example. Let's take a fictitious company, Walkabout. It would be a dog walking service that matches dog walkers with pet owners in need of a walk. The walk's actually for the pets, not the pet owners. So it'd be like Uber for dogs. I use a service not too different from this for scheduling who watches my dog when I'm out of town. I actually could use this right now. So when you look at a typical app like this, this is going to have some sort of mobile component usually. There's going to be a user, so there's a user using the system, that's why it exists. Then you're going to have a series of cloud services that allow this application to function. There's probably going to be an API or website that powers it, some sort of compute layer behind that, almost certainly some sort of database like SQL Azure, some sort of storage, some notifications, and probably some external services that you may not control and that may not be part of Azure for things like, I don't know, credit card charges, other things like that. So let's think about what this system really looks like. There are actually three different aspects of telemetry going on here. The first is the user journey. And this is an important thing to track, especially from a sort of a qualitative standpoint and how your users are experiencing your application. Separate from that is the client app performance. This is also really critical. You can make good decisions or bad decisions based on how your application is performing in the hands of the client. And then finally, there's the service performance, which really encapsulates a whole lot of this. It's easy to say this is one system, but there are really three distinct aspects of telemetry. And it's very tempting to log them in different ways. This actually gets even more complicated because you might think that, well, this isn't too much workload, this isn't too big of an application, it's not going to be doing too much. But if you think about the user journey, so one entry in user journey logging would be booking someone to walk my dog. To do that, I'm probably going to have to interact with the client several times. I'd say probably at least 6 different client app interactions between sending requests and receiving responses, presenting menus to the user, things like that. And then the service backend for that is probably going to have to do 40 different service operations for those 6 requests, so across those 6 requests. So when you look at this, you actually start piling up a tremendous amount of telemetry already. And you've made it even more complicated by having different aspects of telemetry, which are all useful to you. But even for a small application, like for instance this app in one big metro area, you might have 10,000 users who interact twice a day with the application and really produce 47 events per interaction. You're actually talking about 940,000 things to track per day. So that's actually getting to be a pretty big number. This goes from being beyond what you could just figure out really easily and casually to being a bit of a challenge. And now imagine if you didn't have 10,000 users. Imagine if you were in a lot of markets and you had 1 million users. Keep adding zeros onto that, and you actually get into this place where your events will actually trigger a chain reaction of other events, and you can see where that's going to go. Not anywhere good, actually. In the past, most of the logging in our systems, actually, I wouldn't even say past, I'd say current. Currently, most logging is done by each component separately. So you did get some sort of movement a while ago to use logging frameworks, at least on the service side. Those are really useful. But even when you use those, it's really independent logging, independent on each server in the system, independent on each service in the system. And it's really up to the system administrators to collect those logs, to shuffle them back together, and try and make sense out of them to see what's going on. And that can be a big challenge. It usually only happens when something's gone wrong, when someone says it's slow, and you have to start figuring out what's going wrong. So this really makes telemetry and logging in the current context viewed more as a troubleshooting process. And Event Hubs is changing this. Event Hubs provides a centralized logging service that is cloud scale and has built-in partitioning semantics, which is the key to the scale model. This is a partitioned consumer model. So what makes something a partitioned consumer model? It's a model that removes locks. So you're moving away from this central locking and contention model, which would be a competing consumer model, into the partitioned consumer model. It scales out with more partitions rather than up. There's always an upward limit to how high you can scale something, and cloud scale is all about scaling out. So really it's the logical opposite of competing consumers. And anything involving locking, so databases, things like that, are going to be your examples or your typical competing consumers. They'll have a finite point at which they'll scale to. So how does partition consumer work? How does this work in Event Hubs? How does Event Hubs really enable the scale that we claim that it does? Each Event Hub is actually made up of a set of partitions. And each of those partitions actually contains an independent buffer of events within it. Those events are ordered from oldest to newest, and they really are functioning independently. So partition 1 is unaware of the events in partition 2. Event producers don't actually see the partitions normally. They just send events into an event hub. And they have a couple choices about how to do that, actually two choices. They can do it through HTTP or AMQP. And they can also have some other features, like using a partition key to group their events together. Not that they pick which partition those events go to, but that they'll know that their events are always together for downstream systems to consume. This can be really useful for data locality, so that if you need to do stream processing or moving averages or anything like that, all the events for a particular publisher are in the same place. When you're reading out of events, event hubs, reading works a little bit differently. And this is where the partitioned consumer part comes. Event receivers are all readers, they're all consumers, and they all access event hubs through a consumer group. The collection of readers for each partition within an event hub is called a consumer group, and each partition does need a reader in order to read the entire stream. This means that none of the readers are competing with each other to read that stream. They are exclusively reading that stream. You can actually use consumer groups to have multiple sets of readers reading the entire stream. Again, each reader reading one partition within that consumer group. So this enables a sort of a pub-sub semantic for this. It is the responsibility of the readers to keep track of where they are in that stream within that consumer group, within that partition. So each consumer group can have separate offsets that they're reading their streams from. Sending events to Event Hub is very easy also. Here's an example of sending an HTTP post to an Event Hub. I chose this just because it's the easiest to read and because I don't natively speak AMQP, although I'm getting close. So we do have the two protocols here, HTTP or AMQP. Which you choose depends on the usage that you're going after and where in your telemetry stack you're going to be. If you're going to be on the service side, if you're going to do a lot of chatty telemetry, it's almost always a good idea to use AMQP. It's a very sophisticated protocol, the advanced message queuing protocol, that has things like credit-based flow control. It has an open TLS session, so you can send multiple events without having to do a TLS handshake over again. It's really powerful. We do provide the HTTP for ingress, at least, though, because a lot of devices and things and apps use HTTP and know HTTP. And if you're actually doing very sparse communication, like that 2 interactions a day thing from the mobile app, you might actually be better off with HTTP. Here you can see that the post just goes to a specific address. This is my specific event hub in here. I'm setting an authorization header, which is just a SAS token, and a content type. Then I put in some brokered properties. So these are header properties for the message. You can put under this brokered properties any basic type, any primitive type that you like. And you can see the JSON message that I've put in here, which is the HTTP body. Event Hubs doesn't actually look at the body, so we don't do any processing with it. We never crack it open. You can send whatever you want. It can be encrypted. It doesn't matter. It won't change our performance. That's one of the reasons our service is able to scale so well. So when you look at an overall pipeline for processing events in Azure, this is sort of the canonical architecture of what it's going to look like. You're going to have event producers on the one side. These could be applications, they can be devices, they can be other services, and they're going to be sending events to some place to be logged. This can be through direct sends to event hubs, quite common, especially for larger devices or IP-capable devices. They can use cloud gateways to do some sort of protocol translation, perhaps like a web API or something. And then they can also use field gateways for when you get more into IoT-type scenarios, which this specific scenario I'm walking through here isn't, but a lot of our users actually use this for. The next stage in that is event hubs. This is really the ingress service. This is the ingestion broker. It's going to let the messages flow in and buffer them here to protect the downstream components of your pipeline, which are going to be other services. They might be compute you've written yourself. They might be stream analytics, which I'll touch on a little bit later. And then after that, you're going to get to things like long-term storage and presentation to users and actions that you can take on this telemetry. So the important thing to know when you look at a pipeline for event processing is that the pipeline is only as strong as the weakest link within it. And that is why Event Hubs is so important for building a scalable telemetry pipeline. It's because since it's a buffer, it disconnects the upstream, so the ingressing events, from the downstream or consumers of those events. So if you have a flood of ingress, it's not going to overload your egress. Without that, if you don't have something that's a buffer in between your publishers of events and your consumers of those events, you're very likely going to get some pretty nasty scale problems. Things will break in what's the right way to say, inelegant fashion. They'll just sort of fall over. So the first place to start thinking about scale is really in the center of this pipeline, although it's not the only place. You have to think about scale in the entire pipeline. So let's talk about how Event Hub scales. There really are two mechanisms for this. One we've talked about a little bit is partitions. Partitions are set at Event Hub creation time, and they're really not so much about scale in the Event Hub as scale downstream to the Event Hub. The count of partitions is really fundamentally about the maximum degree of downstream parallelism. In more simple terms, I guess that means how many active readers you're going to have reading from that telemetry stream at one time. Recalling that each reader needs to be reading from one partition in order for it to be not a competing consumer, in order for it to be a partition consumer model. So partitions are really more about downstream parallelism than they are about the event hubs. The event hubs themselves are really governed by throughput units. A throughput unit is a variable reserved capacity. It's variable in that it's available hourly. You reserve it, as in you're paying for it before, so you reserve it for that hour or as many hours as you want. And it entitles you to ingress 1 megabyte per second of telemetry or 1,000 events per second. So that's the amount coming in. Whichever those limits you hit first is going to be the limit for that throughput unit. It also entitles you to egress at 2 megabytes per second or 2,000 events per second. So we do throttle on both of these. Throughput units are namespace wide. What that really means is the namespace is sort of the top level container in Service Bus, which is what Event Hubs is part of. So the capacity that you're reserving through throughput units is divided among all the event hubs within your namespace. If you only have one event hub, that makes it pretty easy. It's just for that one. Importantly, overages are throttled, and they're throttled evenly across the event hub, even if you have multiple namespaces or multiple event hubs, and even if you have multiple active readers and writers. It's not that whoever got there first gets all the capacity. It's that when we see that you're exceeding your limit of reserved throughput units, we'll throttle all senders or all receivers based on which metric you're exceeding. So it's a lot of fairness built into the throttling, which is also important for protecting your downstream system and protecting your upstream senders, in fact, so you don't really sort of DDoS yourself with telemetry. How you scale throughput units, there are a couple ways to do this. One is the hourly way that I mentioned. It's through the portal or through a REST call. You can select anywhere between 1 and 20 throughput units. This actually enables you to scale up to 20,000 events per second of ingress. That's pretty big, at 1 kilobyte, 20 megabytes per second of ingress. It's a pretty big amount of ingress. That comes out to 1.6 something billion events per day. So you're already starting to talk some pretty big numbers. If you need more than that, and we do have customers that need more than that, we do grant blocks of 20 throughput units at a time, up to 100. You need to do a support ticket to do this right from the Azure portal. But when you do this, it's no longer a variable hourly charge. It's a fixed charge all the time. One thing to keep in mind, though, is that the throughput units is only part of the cost of event hubs. You also pay for ingress. Ingress actually comes out to be the bigger number. So if you have throughput units and you're not filling them up, it's not really that big of a deal because the bigger number is the actual events you're publishing. Finally, if you need more than that, and we do have a couple customers that do, we have a lot more internally, but we have some public ones. We can talk about options for 250 megabytes per second, 500 megabytes per second, or a gigabyte per second. So if you really need that, you need to work with us. This is not a short-term commitment sort of thing. This does require long-term commitments and partnership and planning, but we can grant you that capacity. So now that you have the basics of how you're scaling a single event hub or a single namespace, let's talk about how you're actually scaling your telemetry pipeline. Again, remembering that the center of that pipeline is event hubs. Really, throughput units are going to be your ultimate capacity cap. So that's going to be your limit. That's going to be what you'll hit first, at least. And it's important to remember that you should size for reasonable expected midterm volume. This is cloud. You can change it. You can't change the number of partitions, but you can create another event hub. Nothing stops you from that. And it's really important not to plan for some sort of maximum optimistic long-term theoretical scale limit that you might hit someday if everything goes great. because why not do that? That's kind of how the mainframe worked. That's a mentality that is trying to scale up rather than out. So this really ties you into decisions that you may not be happy with in the future. And the future is totally unknown to you when you're starting out on building your service, and it will change. So important things to keep in mind: this is software. It should be soft. It should be flexible. Don't try and think about it like hardware. That's kind of one of the dangers of these building architectural analogies that people often use with software. And then finally, let's talk about real scale now. I would think about scaling your telemetry pipeline and your application in general the way that we scale Azure, or at least I can speak pretty confidently to the way we scale Service Bus in Azure. And that's the concept of a scale unit. So what is a scale unit? It's an independent vertical slice of functionality that's built and designed and tested to support a specific workload. So that could be a number of users, number of devices, or an amount of traffic. And it is a complete vertical independent slice. Using a scale unit is a good idea. We do it for a few reasons. One of them is geo-proximity. Especially if you're doing something like an app that users are using interactively, you want to have the latency times to those users be as low as possible. So putting your app in different locations around the world, in different Azure data centers or regions, will make it much more responsive. It also gives you better availability. A disaster in one region might bring down a whole region if it's a big enough disaster, something like an earthquake. But you actually buy some diversification by placing your application around the world. Sort of like investing, the diversification is the only free lunch. And finally, you get the ability to scale both up and out when you use this sort of scale unit model. You can scale up by making an individual scale unit bigger, giving it more throughput units, more compute instances, whatever your resource that you're bumping against you need. And you can scale it out by putting more of those throughput units in the same region or into more and more geographic regions. What does this look like when you actually deploy this? It's pretty easy, and it's getting a lot easier now with our new ARM and our resource providers in Azure. You basically just stamp out the exact application, the exact stack, in different places around the world. So this gives you, again, all those three attributes that I talked about that are going to be really useful for you about availability, about proximity, and about independent scale. And so in this case, this is exactly what this would look like, having data centers spread around the world to where your users are. So how much can you really scale with this approach? Let's just not even get into the call me model. Let's think about just pure telemetry pipeline stuff we've sized our stuff to work in public, so you probably don't have to call anyone before you have to call the Event Hubs team. And let's think about 4 scale units around the world from that previous slide. If you had 12 throughput units per scale unit, so you're talking about a capacity for up to 12,000 messages a second in each of these 4 regions. You're dealing with 1 kilobyte events. You're going to be doing 2.8 million events per minute as your upward limit. That's a pretty big aggregate throughput. And that's going to give you 4 billion events per day and change. So that's pretty big. And if you look at that in data size, since these are 1 kilobyte messages, it's 4.1 terabytes of data. That's a tremendous amount of telemetry. You're very quickly going to reach the point where processing that amount of telemetry is actually becoming more of a challenge than actually acquiring that amount of telemetry. And that's another way that the scale unit model is going to help you. It's breaking a big problem down into smaller problems and solving them independently. You can still aggregate things after the first stage, but this is really the best model to do this with. Next, I want to talk a little bit about reading and processing events. So the first thing I want to cover is Event Processor Host. This is an intelligent agent for reading from Event Hubs that we've built for our .NET clients. We're working on other languages as well. It has some really slick features in it. So it has automatic load balancing, partition management, meaning who owns which partition, and the client-side checkpointing or client-side cursor capabilities that you require when working with Event Hubs. So this framework, this agent, makes this all very easy to work with. And to show you how easy, I'm actually just going to show you the code for this. I don't even need to break into Visual Studio. It all actually fits on one slide in a fairly legible size. What you need to do is implement iEvent Processor. It's a class in the Service Bus library, or an interface, sorry. And it has 3 methods. The methods are close async, open async, and process events async. I think you can gather probably what they mean, and that we take async very importantly, very seriously, because it's really the only way to provide real scale. So you can actually see here pretty simple methods, pretty simple parameters for them. And in a little bit further detail, let's actually go look at what a more realistic implementation of process events async might look like. So you saw on my HTTP request earlier, I was setting a type, an event type in the header called booking. I can actually peek into those properties here. I mentioned we don't open the message body, the event body, but you can see into the properties. And you can use that to drive what sort of logic you're going to implement here. So in this case, I'm looking for booking, and then I'm actually deserializing a JSON object into a .NET class that I know is of type booking. And then importantly at the bottom here, you can actually see that I'm keeping a dictionary of bookings. So I'm doing some duplicate detection in here a little bit, very primitive duplicate detection. And I'm keeping a message count. And then I'm calling that checkpoint async, that thing I talked about before. Checkpoint async is, in this case, with no overload for it, is just going to checkpoint to the last message in that enumerable of event data that came into this call. So it will checkpoint. It'll say to Event Hub, I am confident that I have finished all of the data up to this specific point. And you don't do it at every single message, because you would quickly run into other limits, things like storage limits, about how quickly you're checkpointing. Recall that we are talking about thousands of messages per second, scaled out, even potentially millions of messages per second. So you need to be careful on how you're going to checkpoint. This does give you a lot of flexibility still. This is the way that if your processing stopped and restarted, it would know where to restart on another node. Now that you've got your class, you actually need to host it somewhere. And this is where the host name in event processor host comes in handy, or the host part of the name. Creating an instance of this class is very simple. It takes, 5 parameters. So that's going to be the host name, meaning the name of the machine it's running on. It's usually good to use a DNS name or something for that. You want it to be a unique value. The event hub name, that should be obvious enough. The consumer group name, so that's just a label for your consumer group. The connection string for both the event hub and for storage. And I'd mentioned the storage piece earlier because of storage is not only where we're going to save that offset for each partition reader, it's actually where we're going to use the leasing mechanism of storage to control who is reading from which partition. After you've instantiated the event processor host, all you do is call register event processor async. And this is going to tell the host that this is the class that it needs to instantiate for each partition that it's going to start reading from. And when we look at how that works at runtime, we can see that when something starts up, in this case I'll say a worker, it could be a Windows service, it could be a command line application, it could be anything, and it's got an instance of event processor host. After that register call, that event processor host instance is going to look at the event hub, see how many partitions there are, and try to get a lease on every single partition. And since there's no one else reading it right now, it's going to get a lease for every single partition. After it acquires that lease, it's going to create an instance of your event processor for every single partition. This is subtle and getting sort of important on this point, actually. And then after it has instantiated those, it's going to call open async and then start calling process events async. So this is the point at which the data is coming in. And you might have noticed earlier in that code example that I wasn't doing any sort of thread-safe collections. And that's because I don't need to, because this agent is creating affinity between the instances of your processor and the partitions that it's reading from for that instance. So you don't have to do thread-safe collections. You don't have to do thread management. You're really protected from a lot of that. And in fact, by default, that process events async won't actually get called again until you return from it. So it'll just queue up messages behind it or queue up batches behind it to be processed. So this is a very powerful mechanism, and it helps you keep messages in order. It helps you by avoiding thread locking. It helps you go very, very fast. And then also it scales really well. So when you create a second worker instance or a second command line program or whatever it is you're reading this or hosting this agent in, it's going to do the same thing. It's going to start up. It's going to look at the event hub. It's going to see how many partitions there are and try to get a lease for every partition it can. It's going to see that there are no partitions available. So it will place a reservation for some partitions. It's a greedy algorithm, so it wants all the partitions it could get. And when the first worker comes back and tries to renew its lease for all of these partitions, its leases, it will see some of them it could not renew. and close async will be called on those, and the second worker will now open up on that partition and take over the processing. So this actually scales up, and impressively too, actually it scales back down. So when you step down and go back to just one server, the load redistributes back over. This will happen pretty quick. With only a few servers, it'll happen in, I think the default's like a 30-second cycle. So it'll be a couple minutes. If you have many readers, like 32 or something, it'll take a few minutes, and it'll settle at a pretty reasonable level, reasonable distribution between them. And to see how well this really scales and why this is designed so well for Azure, why this is such core Azure stuff, and I chose worker instances for this. If you make a service, which I did for this, a cloud service, so worker roles that are processing my event stream, and deploy it, you can go into the Scale tab in that service, and you can see that you actually have some scale capabilities that are going to make this even easier for you to use. The best one by far, so far at least, is CPU. And when you think about the type of work you're going to be doing, it could be bounded by CPU or memory or network, but very likely if you're doing heavy compute type stuff, stream processing type stuff, it's going to be CPU bound. And this autoscale capability in Azure gives you the ability to set, as you can see here, how many instances I want running, and then what my target CPU band is. So that's both a lower limit and an upper limit. And I can see that I could set a scale up by, and the wait time to wait before applying that scale again, and a scale down by. What's really cool about this is that you can actually make very expressive shapes of scale, so that you can ramp up very quickly and ramp down very slowly if you are falling behind in your processing. And that's really useful, and it actually gets even more useful because you can have multiple schedules created for different scale times. So for instance, in that same portal, just clicking the Schedules button, you can change to have different scales for day and night, and different scale settings for weekends and weekdays. So these are pretty slick. You can even do independent specific days, so specific holidays or something that you want to have some sort of scale for. This gives you a really good capability of scaling your compute if you're writing your own code and using Event Processor Host, which if you're going to write code, I would strongly encourage you to use Event Processor Host. But now I want to talk about something past this, something past writing code and getting more towards like real cloud PaaS, PaaS to PaaS integration actually, and that is Event Hubs and Stream Analytics. Stream Analytics is one of my favorite services actually. They just GA'd recently, and it's a stream processing service in the cloud. So what's that mean? It's that it's true PaaS, just like Event Hubs. You don't install anything. You don't have to run anything yourself. It's got dynamic scale, much like Event Hubs, which we'll talk about a little bit. It has a domain-specific language that's very elegant. It's based on SQL, and makes it very easy to make expressive statements about processing streams. That language provides, that DSL provides a number of windowing functions that are very useful when doing stream calculations or stream processing, especially for things like anomaly detection or alert detection. And it integrates directly with Event Hubs, which is, of course, my favorite thing. It does use AMQP. Like everything that reads from Event Hubs, it must use AMQP to access it. And this is because it's service to service, and that gives us really good performance characteristics. So creating a stream analytics job is really, really simple. There are really just sort of three things you have to provide it: an input, an output, and a query. Creating the job is really easy. You just go into the portal, click through data services, go through stream analytics, quick create, and you just give it a name. In this case, this is where telemetry changes from how it has been in the past. And this is where it becomes the switching point from having telemetry be a cost center to having telemetry be a revenue center, or something that makes your service interact, better through changes that you can do through the way your systems work, not just in retrospect. So in this case, I'm creating a booking intervention service. So this would be for if I'm having trouble booking, or if a lot of booking events come in a short time window, and that's either because I'm doing something unexpected in the application, or the application's in my hand performing a way I didn't expect it to, or potentially through some sort of fraud. So once you've created your stream analytics job, like I said, 3 steps. You'll see there's no input for it. You just click the Add Input button, and you get to choose if it's going to be a data stream or reference data. This is a very simple job, so I'm going to stick to data stream. You'll see the default on there is Event Hub. That's what I like. It is you can do blob storage as well, but Event Hub's is made for speed. It is made for scale, so it's the default for a reason. And from there, you can actually browse through your Azure subscription and pick which Event Hub you want to read from, and you can actually also provide which policy you want to use. In this case, I'm kind of doing a bad example. I'm using the admin policy. You should make a policy just for your specific listeners. So you can make one that only has rights to listen to your Event Hub, so to read, and that way the Stream Analytics job itself can't actually do anything more to your Event Hub. It doesn't need admin access. And then finally, you get to choose which consumer group. By default, it's going to be one called Default, surprisingly enough. And in this portal, you can actually create a new consumer group. It's generally a good idea to use different consumer groups for each job. And then the last step is that you're going to choose what this input serialization format is. You have a few choices. Here I'm picking JSON because that's what we saw in the messages earlier. And my encoding is going to be UTF-8. And now the query for the ASA job, again, really quite simple. There are a few little things you'll have to learn about it, but not much. If you're at all comfortable with SQL, you do a select. You could actually see these names are coming from, like customer name is actually coming from when the original message. There was a JSON field in there called customer name. It had my name in it. And what I'm doing here is I'm grouping these in a tumbling window, which is a specific type of windowing function, over a 5-minute window, grouping by customer name. And I'm looking for booking events that have occurred more than 3 times in the last 5 minutes. So that's just whatever random logic I've chosen. Now once you have this here, this is actually a really slick part about this. Save your query, and you can actually go back to your input. And you'll notice there's a little highlighted box I've put on there. The highlight's not in the portal. It's the sample data box. This is a way to actually download some of the data in your Event Hub so that you can test with. This is a feature that Stream Analytics provided because they wanted it, and it actually helps out Event Hubs quite a bit too. Do be a little careful. This will let you download a whole lot of data, so pick really what you need, not everything in there if you're writing a lot of data. Then the last step is going to be creating an output for a Stream Analytics job. This is even simpler than the input one. You can pick a variety of sources here, including picking Event Hubs, which is what I'm showing on this screen. I actually like the idea of picking the Event Hubs because it enables sort of a pipes and filters pattern. Too many people, I think, had looked at Event Hubs as first as sort of the center of everything, and it's the big fat pipe for absolutely everything. And in some cases, that's a good pattern, and in some it's not. You might have specific processors or workloads that just want to read a filtered event pipe. And that is actually a great thing to use Stream Analytics for, or to use some sort of filter between the pipes that are Event Hubs, so that you can have downstream readers just have dedicated sort of Event Hubs or streams that they can read from. And then also you get to pick your serialization. So you can change the serialization at this point, or you can keep it how it was. Then importantly, the last sort of piece I want to talk about for Event Hubs is about scaling, or for Stream Analytics is about scaling. The scaling model for Stream Analytics is very, very much like the scaling model for Event Hubs. I don't think that's coincidence. And they basically both go through blocks of 1 megabyte per second of throughput. So on this screen in Azure, you can hit that drop down for streaming units that'll be assigned to that job, and it goes to some big number, bigger than the throughput units does. So 40 something, I think, is what I saw in mine this morning. So it's a pretty slick capability, and you can make jobs for all sorts of things. And like I'd mentioned, this allows you to turn your telemetry from sort of a audit sort of troubleshooting piece that you sort of have to have. Well, if you want to stay sane, at least you have to have, into something that you can really provide new services with. You can really build new things on. These could be failure alerts. These could be anomaly or fraud detections. They could be customer interventions. Really, this is where Azure is making the technology easy for you to decide how to do your business, which is probably not writing the cloud platform, which is what we're doing. So the question is less of more where your telemetry will take you than where you'll take your telemetry. Nice picture of my bike there. And so I'd encourage you to take a look at our Getting Started guides, both for Event Hubs, which are accessible right from the Azure portal, and for Stream Analytics. Also on here is a link for the blog for the Service Bus team. We blog all kinds of fun stuff on there. And finally, my Twitter handle, if you want to follow all the fun Service Bus stuff that we do on the team. Thank you very much. This has been Cloud Scale Telemetry Processing with Event Hubs.